In general relativity or in quantum mechanics, apparent contradictions are a consequence of this wrong view of reality, that there is a classical world out there.
Physics has proven that reality does not fully exist on its own. Experiments have shown that particles do not carry definite properties until the moment they are measured. Even more unsettling, particles separated by vast distances respond to each other in ways that should be impossible. These results were once dismissed as thought experiments, but they were later confirmed in laboratories with real equipment and real data. The findings were so disruptive that they overturned ideas defended by Einstein himself.
Einstein had a criterion for reality, and that is quantum reality. And that's what you see, I don't know anybody's ever stated it quite this way. See, Einstein did talk about an element of reality, but he didn't say, oh, this is a different kind of reality from a normal classical reality, or in the German accent. He didn't say that. I don't think he said that at all.
In this video, we are going to explore how scientists discovered that the universe may not be locally real, and what that means for our understanding of reality.
This comes, I think, from the fact that quantum physics tells us that some of our everyday way how to look at the world are wrong. What is wrong is the assumption that, for example, every object has to be at a definite place at any time. This is not true anymore. Some people say that a particle can be at two places at the same time, which again is not good language. The good language is that there are situations where it is completely undefined where the particle is, and it's not even us who do not know, but the particle itself also does not know, so to speak. So this is an objective non-existence of a feature of reality. And that is new in quantum physics. That does not exist in what we call classical physics, the physics before quantum physics. It is also not true in relativity theory, by the way. There we also have a well-defined space, a well-defined time, well-defined locations, and this kind of objects.
On October 4th, John Clauser and Anton Zeilinger, together with Alain Aspect, were awarded the Nobel Prize in Physics for experiments that changed how we think about the physical world. What their work made clear is that one of the simplest assumptions we make about reality, that objects have definite properties that exist regardless of whether we look, cannot hold together with the other assumption that nothing can affect something else faster than light. This sounds abstract, but it is the kind of basic idea that shapes how we build models of the world and how we design machines that use quantum effects. The phrase people often use for the combined idea is local realism. Locality says events at one place do not instantly affect distant places. Realism says physical properties exist and have definite values whether or not anyone measures them. Combine the two, and you get a tidy picture. Things possess values and only change when influenced by nearby causes. The trouble is that, at the scale of atoms and photons, experiments have repeatedly shown that the tidy picture fails. The results favor the predictions of quantum theory and force a choice about which intuitive assumption to give up. To see why this is such a big deal, go back to the 1930s.
Now, you go back a few decades, then I think you could say that the interpretations of quantum mechanics are very interesting and very important because we're talking about the nature of reality. But you might say, well, it doesn't really matter so much practically, right? Now, I have a lot of colleagues in physics who would, I think rightly, hate that description because what we're trying to do is understand reality, what physics is. But now, particularly, I think, with the possibility of building quantum computers. This attempt to understand how large systems of quantum mechanical objects behave is becoming extremely important, because a quantum computer is a device which is built out of qubits. So remember, a qubit, an example would be an electron, which has this property that when you make an observation of the spin, let's say, of this electron, it behaves like a coin. It can be up or down, heads or tails, however you want to describe it. But that thing can also exist in a superposition, a combination of these things. And it's a perfectly valid configuration. And you use that. That's the kind of property that you use in building a quantum computer. You can also then ask the question, well, what happens if I get another one, two electrons together? These can be in what's called an entangled state. So then you have a much richer structure of this physical system.
Quantum mechanics had matured into a practical tool that made excellent predictions. It also produced strange statements. Particles behave as waves, and objects seem to lack definite properties until measured. Einstein, Podolsky, and Rosen pushed back in a paper that asked whether quantum mechanics was complete. Their thought experiment used pairs of particles that could be measured in different ways. If you measure one, you can predict the result of a corresponding measurement on the other. Einstein and his colleagues thought that suggested quantum mechanics might be missing something, some extra hidden variables that would restore the classical picture. For decades, the debate sat in an uneasy truce. Quantum mechanics worked and made correct predictions, but the idea that it might be incomplete left the door open to alternatives. Then, in 1964, John Bell found a way to test whether local hidden variables could reproduce quantum predictions. Bell's insight was to derive an inequality that any local realistic theory must satisfy. Quantum mechanics predicts violations of that inequality under certain conditions. This moved the discussion from philosophy to experiment and set a clear target for laboratory work. The early experimental tests came in the 1970s. Clauser and Frederick Friedman performed one of the first of these experiments in 1972 and found results that favored quantum mechanics over local hidden variables. Clauser and colleagues then formulated a convenient inequality with collaborators known as the CHSH inequality, which allowed clearer tests and made the problem easier to implement in the lab. Alain Aspect later improved the experiments in the 1980s by closing some experimental weaknesses. His 1982 experiments used fast switching of measurement settings while photons were in flight, so the choice on one side could not have influenced the other by any ordinary signal traveling at or below light speed. Aspect's results matched quantum predictions and tightened the case against local hidden variable alternatives. To make the conceptual points concrete, consider a simple thought experiment with light and polarizers. A beam of light can oscillate in many directions. If you place a filter that only allows vertical oscillations, only the vertical component passes. If you rotate the filter by 90 degrees, you block what the first filter would let through, and no light emerges. That matches everyday sense. The unintuitive part comes when you add a third filter in between the two. Under certain conditions, a little light that was blocked before reappears after adding the middle filter. That happens because measuring a photon's polarization changes the state of the photon. Measurement is not a passive act that simply reads a pre-existing value. It alters what can be known and what will happen next. Now translate the polarizer story to two separated particles. Entanglement creates a pair whose properties are linked. You cannot fully describe one member of the pair without referencing the other. If you measure a property on the first particle, you can predict or constrain what a measurement on the second will yield. Bell's inequalities give a precise, testable form to the intuition that hidden instructions assigned to particles at birth could explain their later agreement. If those instructions were enough, the statistics of many measurements would satisfy certain bounds. Quantum mechanics, predicts, and experiments show violations of those bounds under well-chosen measurement settings. That is the central empirical claim that toppled the simple package of local realism. A series of experiments across decades reduced the options available to defenders of local realism. Clauser's early work and the CHSH formulation translated Bell's idea into practical measurements. Aspect added crucial technical improvements. Later, different groups pushed further by improving detectors, randomizing measurement choices in more secure ways, and increasing separation distances between measurement stations. In the last decade, experimental teams produced what are called loophole-free Bell tests that addressed the main technical gaps simultaneously. Those tests used high-quality detectors, fast and well-isolated random number generators for choosing settings, and spatial separation sufficient to rule out ordinary communication as an explanation for the correlations. The collective weight of the data strongly disfavored local hidden variable theories. What does it mean, then, that the universe is not locally real? It means that at least one of the two assumptions must be wrong. Either the world allows influences that act faster than light, or the properties we study do not have definite values until they are measured. Many physicists accept the second possibility. They treat the wave function or quantum state as the full description of a system, not as a shorthand for unknown variables. In that view, particles are not carrying pre-assigned results when created. Instead, outcomes arise in the interaction between the system and the measurement apparatus. That answer might sound unsatisfying because it seems to make reality depend on observers. The more precise scientific reading avoids mystical language. It does not require a conscious mind to collapse the wave function. Experimental setups use detectors, polarizers, and noisy electronics. These devices interact with a quantum system and cause a particular result to become recorded in a macroscopic way. Saying that measurement matters is a statement about interaction and about the transition from fragile quantum amplitudes to robust classical records. It cuts against the idea that every property lies, fully formed, waiting to be read off by a measuring device. There are other ways to respond to the experimental facts. One is to keep realism and accept non-locality. David Bohm developed such a theory where particles have definite positions and are guided by a wave-like field that connects distant particles. Bohmian mechanics reproduces quantum predictions but introduces an explicit non-local mechanism. That option sacrifices the locality intuition rather than realism. Another route is to accept the wave function as the full account of reality and build interpretations around that. The Copenhagen family of views, with many variations, treats the wave function as central and measurement as a primitive action that yields definite outcomes. The many worlds interpretation takes a different tack. It keeps locality and determinism by allowing the universe to branch into many non-interacting outcomes so that every possible result happens in some branch. In many worlds, there is no collapse. Measurement splits the world, and correlations are explained by common history rather than immediate influence. Less mainstream options also exist. Superdeterminism preserves both locality and realism by denying the independence of measurement choices. It proposes that the settings experimenters choose are not independent of particle properties, perhaps because both are the result of deeper correlations stretching back to initial conditions. That view avoids Bell's contradiction, but at the cost of accepting a kind of cosmic prearrangement that most people find unappealing. Retrocausal models try to explain correlations by allowing effects to travel backward in time so that future measurements influence past states. These models are subtle and hard to fit with standard relativity, but some researchers explore them as alternatives to overt non-locality. The experimental facts have practical consequences. Entanglement is not only a philosophical oddity, it is a resource. Quantum teleportation protocols move quantum states between places by consuming entanglement and using classical communication. The first lab demonstrations of teleportation date back to the late 1990s and showed that quantum information could be transferred reliably in a laboratory setting. These demonstrations led to longer and more robust teleportation links in later work, including experiments that transmitted quantum states between islands and across urban distances. Entanglement also underpins quantum key distribution, which allows two parties to share a secret encryption key with security guaranteed by the laws of quantum mechanics. In short, the same correlations that refuted local hidden variables are the building blocks of a new class of information technologies. It is important to be precise about what experiments show and do not show. Violations of Bell inequalities demonstrate that no local hidden variable model can reproduce the observed statistics. They do not show that information can be sent faster than light in a controllable way. Quantum correlations are stronger than classical ones, but they do not enable controlled superluminal messaging. The randomness at the heart of measurement outcomes prevents researchers from encoding meaningful signals into the correlated outcomes in a way that would violate the relativistic speed limit. Every experiment has assumptions and potential weaknesses. Early tests had problems like detector inefficiency and the possibility that measurement settings were known in advance at the source. Over time, experimenters addressed these by building faster switches, improving detectors, increasing separation distances, and randomizing settings with processes that are hard to predict. The post-2010 generation of experiments closed the major practical loopholes in the same runs, leaving only exotic alternatives like superdeterminism that require truly far-reaching assumptions to survive. Beyond the strict question of locality and realism, the work touches on deeper questions about the nature of explanation. Classical physics offers an account where causes and properties sit comfortably in space and time. When quantum correlations refuse to fit that mold, what replaces the old way of explaining? Some researchers adopt an instrumentalist stance. The theory predicts correlations, and that is enough. Others seek a clearer ontology, even if it costs locality or demands a huge multiplication of worlds. Some focus on finding new principles that might constrain or explain why quantum correlations have the form they do. Still others explore subtle connections to gravity and cosmology to see whether larger-scale physics might affect the picture. The phrase, "the universe is not locally real," can sound like a final verdict about the structure of everything. It is better to view it as a constraint. Clauser, Aspect, and Zeilinger did not end the debate. They reframed it and gave clear experimental targets that made the discussion productive rather than purely speculative. Their work shifted entanglement from paradox to practice and opened the way for quantum engineering, as well as further foundational work. Thinking about the question, "Is the universe locally real or infinite?" invites a second meaning of infinite. If by infinite we mean that the web of quantum connections stretches without bound, then entanglement hints at a kind of non-local connectedness that is not limited by ordinary distances. Entangled particles can be separated by kilometers or more, and the correlations persist. In that sense, quantum mechanics suggests a network of relations that does not weaken with distance in the same way classical forces do. If by infinite we mean spatially infinite, that is a separate cosmological question. Measurements of cosmic geometry probe the large-scale structure of the universe and suggest the observable universe is very large and very close to flat, which allows but does not force the full universe to be spatially infinite. Cosmology and quantum foundations intersect in deep ways, but they are distinct research areas with different data sets and methods. The story shows how science advances. Einstein raised a sharp challenge. Bell converted a philosophical question into a testable inequality. Experimental groups, including Clauser, Aspect, and later teams built experiments that pushed down technical objections. Each step exposed new details and opened new possibilities. What began as a debate about thought experiments became a set of lab techniques that engineers now use to build devices. That development transformed entanglement from an oddity into a tool for secure communication and the core of proposals for quantum networks and processors. The story does not stop with lab results and prize ceremonies. It moves into questions people can work on and technologies people can build. One clear direction is scaling up. Entanglement has been shown with single photons and small collections of particles for decades. Researchers now try to entangle larger systems and keep that entanglement alive longer. The goal is not to prove the same basic facts again. It is to find the boundary between quantum behavior and the ordinary world we live in. If that boundary is sharp, we might eventually control it. If it is fuzzy, that tells us something important about how classical reality emerges from quantum rules. Another active path is building a quantum internet. Today's networks move classical bits. A quantum network would move qubits, meaning quantum states, between nodes. Entanglement is the resource that makes quantum networking possible. Engineers have shown short links that teleport quantum states over fiber and free space. The hurdles are not just keeping states intact. They include synchronization, repeaters that preserve entanglement over long distances, and hardware that can operate reliably in real-world conditions. If those challenges get solved, we will have secure communication links and distributed quantum computers that share work across devices. That would change computing and cryptography in ways we are already starting to model. Philosophy and public debate have not gone away either. When experiments rule out a simple package of local realism, people ask what we should believe. Scientists answer with different models based on what they want the theory to do. Some want a clear picture of what exists independent of measurement. They may accept non-local laws that link distant parts of the world. Others want to keep locality because it fits with relativity, so they accept a picture where outcomes are not fixed until they are recorded. Both moves change how we explain physical processes. That is normal in science. Experiments tell us what picture is consistent with data. Theories are judged by what they explain and how well they predict new things. New experiments keep testing corners of the problem that are still open. Teams now use cosmic sources as random number generators to pick measurement settings. The idea is clever. If the choice of how to measure depends on light from distant stars, it is harder to claim that local hidden variables manipulated those choices. Other groups test Bell inequalities with systems separated by bigger distances and with more massive objects. Those tests push the question of where non-classical behavior ends and everyday classical behavior begins. There are also deeper proposals that try to connect quantum foundations to gravity and cosmology. Gravity is weak at the scale of particles, but it is universal. If space-time itself has quantum features, then experiments that probe entanglement under different gravitational conditions might reveal new effects. Some thinkers suggest that space-time and entanglement are related at a structural level. Those ideas are speculative but testable in principle. If experiments ever show that gravity affects entanglement in an unexpected way, that would point to new physics at the overlap of quantum theory and general relativity. The social and ethical sides matter too. Technologies built on quantum principles can be powerful. Quantum encryption can protect privacy in new ways. Quantum computing may break some current encryption systems while enabling new ones. That creates a need for planning, standards, and education. The same careful test and verify approach that settled debates about local realism should guide how we deploy quantum tools in the world. Some places in the story remain murky. Interpretive pluralism survives because experiments constrain but do not uniquely fix an overall worldview. Superdeterminism, retrocausality, many worlds, and Bohm-like models are not all equally appealing, but they are logically possible if one accepts their trade-offs. Deciding between them may take new ideas or new kinds of experiments that highlight subtle differences. That search is part of the healthy tension between theory and data that drives physics forward. One clear lesson from this history is modesty about intuition. Einstein's intuitions about how the world should behave were powerful and guided decades of good work. But they were not final. Careful thought, clever inequalities, and persistent experiments gave a different picture. That is how science refines our ideas, not by flipping a switch, but by testing assumptions, finding where they fail, and building better models. The result is not chaos. It is a refined map. That map tells engineers where to build and tells thinkers where puzzles remain. If you enjoyed this video, let us know what you think in the comments. If you found it useful, give it a like so more people can see it. And if you want more videos like this, make sure to subscribe and turn on notifications. Thanks for watching.